Good afternoon, ladies and gentlemen. I'm Samuel Estalarias, and I will present an abstract of my work entitled Distribution of Cope Sections in the Hilbert Modular Orbifold. I realized this work as a PhD student at the Universidad Nacional Autónoma de México. I have divided this presentation in 4 steps. We will begin with an abstract, then settings, main results, and the classical case of the modular orbifold. So let K be an algebraic number field, and let M be the Hilbert modular orbifold of the algebraic number field. Let NQ be the probability measure uniformly supported on the cost cross sections of the Hilbert modular orbifold at height Q. We generalize a method of Sadie and show that NQ distributes uniformly with respect to the normalized hyperbolic measure M on the Hilbert modular orbifold as Q tends to 0, and relate the rate by which NQ approaches M to the Riemann hypothesis for the Dedekind zeta function of the algebraic number field. So the setting is an algebraic number field of degree n. This degree is writing like R1 plus 2R2, where R1 is the number of real places and R2 is the number of complex places of the algebraic number field. And we also have the ring of integers of the algebraic number field. We also have a Riemannian manifold or symmetric space formed by the product of R1 hyperbolic planes and R2 hyperbolic spaces, and the Hilbert modular group acts properly and discontinuously on this symmetric space by a formula related with the Mobius transformation. If the number field K has class number H, then the Hilbert modular orbifold has H cost, and each cost can be parameterized by the standard cost at infinity. Therefore, we have an orbifold which has a finite number of n's or costs, and also from the geometry of the Hilbert modular orbifold, it follows that for each cost and each real number bigger than 1, we have a generalized closed orosphere, which is essentially a transversal sections to the costs, and therefore it's of codimension 1. We can define probability measures which are uniformly supported on this transversal manifold, where uniformity means that it's uniformly supported with respect to the Riemannian metrics inherited from the ambient space. So we normalize it to these measures to be probability measures, and we sum the H probability measures that we have. So the principal result of this work tells us that the measures MQ are uniformly distributed with respect to M as Q tends to 0, and this tells us that the submanifolds or transversal sections of codimension 1 are uniformly distributed in the Hilbert modular orbifold when the volume increases. Therefore, we have a picture like this. So here we have the Hilbert modular orbifold, and we have a manifold of codimension 1. We have H submanifolds of codimension 1, and when we sum it up, these transversal manifolds of codimension 1, we see that they start to cover the Hilbert modular orbifold when the volume increases. Finally, we also have a result that relates this with the Riemann hypothesis for the Dedekind zeta function of the number field, and this relation tells us that if the rate of approach of the measures MQ are uniformly distributed with respect to the measures M at certain speed, if and only if the Riemann hypothesis for the Dedekind zeta function of the number field K is true. Finally, we have the classical case of the modular orbifold, which is a theorem proved by Donsadier, which is the beginning of this work. We have then the modular orbifold. We have a closed autocycle, and another one which is of bigger length, and it starts to enrolls in the modular orbifold. And when the volume gets large, when the length gets larger, the autocycle starts to cover the whole modular orbifold. This is related to the Riemann hypothesis, as Sagies shows, and finally it's also related with the prime numbers that I have pictured here with MAH numbers. There is an excellent video with a simulation in the case of the hyperbolic planes that shows the distribution in the classical modular orbifold. We want to thank Professor Alberto Berhovsky-Solá for suggesting the Sagies distribution theorem in the Hilbert modular orbifold and for all his great explanation on this remarkable subject. I'm Samuel Estalarias. Thank you very much. See you later.